All right, so now that we've played around with some of the examples, let's actually tackle our first theorem, right? So we've talked about the basic rules of vector arithmetic and the properties of vector operations. So here we have a theorem that talks about the general properties of vector operations, and we're going to prove some of the results. And I'm going to encourage you guys to tackle the other ones on your own at home. So here we have theorem 2.1, which talks about the properties of vector operations. All right. So I'm going to start off by calling U, V, and W our vectors in the plane. Actually, we should make all this red, right? We've got another rule here. All right. So U, V, and W, these vectors in the plane. And let R and S be scalars. So just round numbers. All right, so then we've got some properties here. The first is the commutative property of addition. That says that the sum of two vectors, the order can be swapped. This is our commutative property. Of addition. All right. The second one is our associative property. If you are trying to add multiple vectors together, then it doesn't matter which two you add first, because they're all going to be the same value. So the sum of U and B and W is equal to B plus the sum of V and W. We can place our parentheses. This is our associative property of addition. Property 3 is the fact that we have an additive identity. There is something that we can add to our vector, right? 0. And we'll get back the vector itself. This is our additive identity property. All right, and we also have an additive inverse, which means that if you give me a vector U, I can find negative U, so that when you add them together, you get the 0 vector. So this is our additive inverse property. All right. It's 5, we have an associated scalar multiplication. So if we are trying to multiply our vector by a scalar or two scalars, then it's fine to multiply the scalars and then multiply them into our vector. So this is our associative property. Of scalar multiplication. And notice it's interesting, we don't seem to have any other vector multiplication so far, right? These are just our multiples of scalars, which are our real numbers. Right. Property 6 is our distributive property. So if we are taking the sum of two scalars and multiplying it to a vector, then what we can do is distribute the vector to our scalars and then do the addition. This is our distributive property. Of vectors over scalars. And similarly, if we are trying to multiply a scalar to a sum of vectors, then we can distribute the scalar into the vectors before we do the addition. So R times the vector U plus V is equal to R times the vector U plus R times the vector V. So this is the distributive property of scalars over vectors. All right, and finally we have an identity of multiplication and zero property of multiplication. So this number 1 times our vector is always equal to the vector, right? So that's our identity of multiplication of scalars. And similarly, 0 times our vector is going to give us 0. And this is our number 0. All right, so 0 times the vector is 0. All right, so this is our 0 property. All right, so let's see, how do we even know if these are true? So, I've noticed that we don't have any multiplication of vectors listed in our properties here. So that tells me probably something's going to be different about that. So let's actually talk about the proof then. So the proof of the commutative properties first. I'm only going to touch 2 of them in the notes. Again, I encourage you to work on the others on your own. All right, so the proof of the commutative property of addition. All right, so if we are interested in letting u equal x1 comma y1 and z, our vector, equaling x2 comma y2, then the sum of those two vectors, well, as we just indicated in the definition above, we add vectors by adding their components. So the x component of the sum would be x1 plus x2, and the y component of the sum would be y1 plus y2. Right, so this is by the definition of vector addition. Now, fortunately, we have a commutative property of real numbers. And the commutative property of real numbers says that x1 plus x2 is the same thing as x2 plus x1. And the sum of y1 and y2 is y2 plus y1. This is by the commutative property of addition of real numbers. All right. And now if we were interested in separating those components again, we see that the first components we have is x2 and y2. And the second components that we have are x1 and y1. Right, so this is once again by the definition of vector addition. And when we look at these, x1, x2, comma y2 is our vector v, and x1, comma y1 is our vector u. And so we've started with the sum of u plus v. We've taken a look at the definition, the regular properties of real numbers, the definition of vector addition again, and we've shown our commutative property. So without that commutative property of real numbers, the statement wouldn't have been true. All right, so let's now take a look at the distributive property. Okay, of scalars over vectors. So if we have a scalar r times the sum of u and v, then we know that what we're looking at is similar to up above. We know the sum of u plus v is the sum of their components. Let's set to r times x1 plus x2, comma y1 plus y2. Right, so once again, this is by the definition of scalar addition. Sorry, vector addition. Excuse me. All right. And now, since we know how to multiply scalars and single vectors, this is what we'll get, right? The R in both components. So this is by definition of scalar multiplication. That was covered in an earlier video. All right, so thanks to the distributive property of real numbers, I can take that R, right, and distribute it right into my parentheses. So that's going to give me Rx1 plus Rx2, Ry1 plus Ry2. So again, this is by the distributive property of real numbers because we're dealing with the inside components that are just real numbers. So without that distributive property of real numbers, we wouldn't be able to do this. All right. Now we know about the vector addition definition once again. So I can separate the sums as individual vectors. So this is Rx1 comma Ry1 plus Rx2 comma Ry2. Right, so this is just, again, by our definition of vector addition. All right, and now I can actually pull out the R. So if we undo our scalar multiplication, we're going to get Rx1 Y1 plus Rx2 Y2. Right, so once again, this is by the definition of scalar multiplication. All right, and then x1, y1 was our vector u, and x2, y2 was our vector v. This equals r vector u plus r vector v. And we've gone ahead and we've proven the distributive property of scalars over vectors. All right, so there are quite a few other properties that are to be proven. So go ahead and tackle them on your own. In fact, our checkpoint is to prove the additive inverse property. So why don't you go ahead and try that on your own. Prove the additive inverse property.